Hi, welcome everyone. If you're here, you're a data scientist or a machine learning engineer who's either looking to get started on building, training, and deploying models using geospatial data, or you are a product manager, geospatial analyst, executive looking for inspiration on use cases that can be done with geospatial ML, or you are a data scientist and machine learning engineer expert who's already building, training, and deploying models using geospatial data, but you're spending months or weeks to build these models and make inferences. And you're looking for ways to bring that time down to days. Cool. Let's dive in. In this session, we'll talk about what is geospatial data, how are customers using geospatial data with machine learning across different use cases and industries. We'll spend 5 to 10 minutes on that, and then we'll transition into what does geospatial ML workflow looks like, what are the key pain points, what are the new capabilities that we are launching today to help you make smarter and informed decisions quickly. Then Shang, our amazing data scientist, is going to come here, show us these capabilities live in action, and bring all these features to life. And then Damian from Arup, which is one of our customers, they're going to come here and talk about how they are using SageMaker Geospatial capabilities to help city planners and developers make better decisions so that they can build better, sustainable, and resilient cities. And we'll leave some time at the end for Q&A. Geospatial data consists of aerial and satellite imagery and map data. Aerial and satellite imagery contains information, visual information and non-visual information that's captured through different types of sensors, camera, LiDAR, radar, and so on. Visual information is very similar to the information that you capture from your iPhone, red, green, blue bands. And non-visual information is the information that's collected through infrared radiations like thermal emissions, gas emissions. Customers use hundreds of terabytes of satellite and aerial imagery to extract meaningful information like building footprint, road networks, and even lane markers on road, and store them as map data. Map data also consists of information that's emitted from your smart devices around you, your iPhone, Ring doorbell, Alexa, car, or even traffic lights. Map information also consists of the information that expresses the neighborhood around you. And you use that multiple times of day to find a restaurant, gym, or a coffee shop near you. In the last decade, 2 major transformations that we see had the biggest impact on the industry. First, the prices to launch and operate a satellite that can capture the information across Earth's surface dropped from tens of millions of dollars to less than $1 million. And 2, nearly every device in the market today is capable of emitting location data. All these devices that we talked about, iPhone, Alexa, car, traffic lights. This is unlocking completely new ways of how customers think about this data, what information they can extract from it, and who can use this data. Let's take a look at some of these use cases where customers are making decisions with a button click that otherwise would have taken them 2 to 3 weeks. For example, first, insurance companies. Insurance companies are now using aerial imagery to remotely assess the characteristics of your property. They can identify roof health, building height, presence of a pool, or overhanging trees to issue you a right insurance quote. They can also verify and validate these insurance claims post a natural disaster and issue funds to end customers who need them the most at that moment. They're also using this information. They're also using the information from some satellite images to assess flood risk, wildfire risk to your property, and sharing that information with the end customers so that they can prepare themselves better. Second, commodity traders. Commodity traders are always speculating prices for commodities over next month, quarter, or a year. And they're looking for that additional signal that can give them a slightest edge over their competitors. Now, they're using satellite imagery to capture weather anomalies, supply chain information, inventory levels, and production activity so that they can forecast demand and supply. And they're using this information to predict prices and get that edge over their competitors. Third, governments are using this information to inform policies for climate change and to hold companies and other countries accountable. They're also using this information to track deforestation, illegal mining, and to manage events post-natural disaster, like floods. City planners and developers are our fourth persona. They're using this information of satellite images to find areas for sustainable development within a city and to measure the greenness of a city at scale, and then use that information to expand the green areas in the city. Agriculture companies are using this information to monitor health of plants across the globe and sending recommendations to farmers so that they can use this information to improve crop yield for their farms. And they're also sharing this information with central governments so they can use that information to prepare themselves better for food security. And we have retail customers that are using this information to bring the information of neighborhood, foot traffic, competitor location, all of it together to find the next optimal location for starting a new store or to optimize the capacity of existing stores. In spite of geospatial and satellite data becoming easily available, the use of this data remains really small in machine learning, in spite of all these use cases. Let's take a look at what does geospatial ML involves and what are the key challenges. Geospatial machine learning workflow today is time-consuming and expensive and requires specialized skill set. First, data scientists and machine learning engineers need to build connectors to access geospatial data, satellite image, and aerial images from open data sources. These are often freely available data, but you need to build out specialized connectors that can ingest data at scale. And if you're working with a third-party vendor, you need to negotiate deals. Make sure you have the right license data. And then you have to build connectors for each of these vendors because most of the times they have different formats. This can take weeks or months even before you're getting started on machine learning workflow. And often, getting access to this data isn't enough. You need to transform or enrich this data. So if you're working with GPS coordinate, in itself, those latitude and longitude information don't have much context. You either need to augment that information with addresses, or you need to augment that information with the road information where these GPS coordinates were collected. And if you're working with satellite images, then you need to clean this data before it's ready for machine learning. Satellite images often have clouds, so you need to either mask those clouds or remove those clouds and restore ground information so the data is clean. Or you need to rescale those images, calculate time statistics, other spectral indexes. And you need to build those geospatial operations that can run at scale, process multiple terabytes of data, and with high reliability. All of this takes weeks of effort, even before you have started machine learning. And that's not enough. Once you have this data, now you need to create a high-quality label data set to train this model. You need to go find a vendor that can create a label data set with you, work with them, create a small data set, verify the accuracy, then go build really high-quality data set. All of this has already taken months before you can make a single inference from this model. And that's not enough. Once you have model inferences coming out of this model, you need to put them on a map to analyze and explore relationship between these predictions, because it's all about geospatial data. And data scientists often have two options. One, to use open source tools, which give you great static images where you can throw in predictions, but you can't really understand the relationship between data. Even to collaborate with non-data science team members, now you have to use Slack, Chime, or your favorite instant messenger, and you are the person who's answering every single question, and you become the bottleneck in the organization. And if you have specialized tools, then your organization has probably deployed an army of engineers to build and host these tools. And there's an ongoing maintenance cost to just visualize these predictions and share with other members. And this does not really bring value to the end customer. Data scientists and machine learning engineers that are working on geospatial data are solving one of the most pressing problems of this century, climate change. They deserve better tools. Today, this is changing. We are introducing new geospatial capabilities for SageMaker. These capabilities will address some of the pain points that we talked about in the last few slides. These capabilities will make it easy for data scientists and machine learning engineers to build, train, and deploy models using geospatial data. Let's dive in to the key features that make it easy. First, We talked about how data scientists and machine learning engineers have to build out integrations with open data sets. SageMaker now comes with pre-built integrations to access open data. We have pre-built integrations for most commonly used data sets, like Sentinel-2, Lancet 8. They are already hosted on open data on AWS, and now with just one API call, you can access this data. You can filter out the data. If you are also working with one of the third-party providers that we have partnered with, like Planet Labs, then you can bring the data into Amazon Simple Service Storage, and from there you can bring into SageMaker using the integration that we are shipping today. So with just one API call, you can start to access this data. You don't need to build out any more integrations for weeks or months before you can get started. And we understand that you probably have proprietary data formats or other vendors. So you can still continue to build those connectors. And if you already have those connectors, you can simply migrate your notebook and start to leverage features that we have built today. So this makes migration very easy and seamless. As we dug into the problem of unlocking access to geospatial data, we learned every organization is also running geospatial operations that process this data. And most of these data science teams are working in silos. For example, one of our customers was working on New York data. There were multiple data scientists in the organization that would often query New York data over the last 5 years. They remove clouds from it and get started. They would lose just weeks trying to do the first step in the process. If you're using one of the operations that we are shipping today, then if you run those operations, we catalog the output of the data and make it available to everyone in your organization. This means if once somebody brings down New York data set, removes clouds from it for the last 5 years, that data set is now available and visible to everyone in your organization. This improves productivity and reduces cost for your organization. For transforming and enriching this data, our customers have built homegrown tools over years, or they've been using SageMaker Studio notebooks and installing open source geospatial libraries to process this data. To make it easy for you to migrate your code base to new geospatial capabilities, we are shipping a new geospatial image for SageMaker Studio notebooks. This image comes pre-installed with geospatial libraries. One of the big complaints we heard from our customers was when they had to install these geospatial libraries, they would often have to verify open source licenses, go through security policies, checks within the organization before they can take these open source libraries to production. Now, these open source libraries come pre-installed in the image. So you can start to leverage them as if it was just another import statement. You can simply migrate your code and it will work seamlessly. And then slowly and gradually, you can start to adopt the new operations that we are shipping. We are shipping 2 types of operations. First, we are introducing a concept of Earth observation jobs inside SageMaker. Now, these Earth observation jobs allow you to process satellite data. They've been purpose-built so that any connectors that we have built, you can bring the data easily and process them with these Earth observation jobs. You only need to provide 3 inputs. 1, area of interest. So in the case we talked about New York, you will provide an area of interest of New York. Second, the time range. So we talked about 5 years, so you specify 5 years. Third, the type of operation you want to run. Spectral index, or changing the resolution of the images, or removing cloud cover, and restoring ground information. With just 3 arguments, you can kick off an Earth observation job that will process all the data. We will take care of taking the satellite data, splitting it into different machines on the cluster, combining them, giving you an output, and also make that data set available inside SageMaker, so everyone in the organization can see it. And if you're working with GPS coordinates, one of the big challenges with GPS coordinates was to augment that information with addresses or to augment that information with road data. You had to build integrations to bring that information in. We are now shipping APIs that you can kick off and start to augment these GPS traces with addresses or road segment information. Not only are these APIs able to augment this information, they are specifically catered to data science and machine learning engineer experience. They take tens of thousands of GPS coordinates or tens of thousands of drives at the same time where these GPS coordinates were collected to augment this information. So these APIs are specifically targeted for data science and machine learning persona, and they help improve productivity by weeks. Once you have cleaned up your data and you're ready to go, you can now need to start training a model. We talked about challenges that you often have to, before you can even get started and make predictions, you have to create data sets. So what we are doing is we are shipping state-of-the-art pre-trained models for some of the table stakes feature that are involved in every single geospatial ML workflow, like masking cloud, removing cloud cover, or classifying the land as each pixel in the satellite image as land, vegetation, snow, and so on. All of this you can do with pre-trained models that we are shipping. Second, we understand that the pre-trained models that we are shipping will not cover the breadth of use cases that you have. So you can still continue to build high-quality data sets. Now you can leverage SageMaker Ground Truth or SageMaker Ground Truth Plus to create high-quality labeled data sets and access them inside SageMaker to kick off a training job. We also understand that you have already built out models. You're using them for making predictions, so you can simply migrate those models to SageMaker and get started today seamlessly. One of the big challenges we talked about was data scientists often become bottleneck in the organization to often answer every single question about this data, about the relationship with data. Now, we are shipping an interactive map that is embedded inside the notebook. The same map is also available outside the notebook. So you, data scientists, can visualize satellite images or millions of vector data points or GPS traces all in one map, explore relationships, share with other members of the team. And these tools are powerful enough that they can render millions of data points and make collaboration easier. We expect that this will save you weeks or months of effort. One of our customers from agriculture vertical, Zarview, that's a precision agriculture firm. They use satellite images to monitor health of the plants and make recommendations to farmers to help them increase the crop yield. They onboarded SageMaker Geospatial capabilities a couple of months ago, and they've already improved their efficiency by 50%. We look forward to you trying these geospatial capabilities. Yeah. On that note, I'll hand over this presentation to Shang, who is going to demo this tool set and all the capabilities and bring these features to life.
Hi, I'm Xiong Zhou. I'm an applied scientist working for the SageMaker Geospatial. Today, we're going to walk through a quick demo of SageMaker's new geospatial capability, which makes it easy to build, train, and deploy your machine learning model using geospatial data. We will focus this session using machine learning for climate change monitoring. Specifically, we will look at the Lake Mead to see how the Lake Mead has been shrinking over the past few years. Before we run through the notebook, make sure you have the necessary policies attached to your notebook instance. Lake Mead is the largest reservoir in the US. It supplies water to over 25 million people in the US. It is located in the state of Arizona and Nevada, only 24 miles east of Las Vegas. Fun facts, since 1937, Lake Mead has been shrinking for over 80 years. Now it's at the lowest. So in this demo, we will show you how can measure the surface area in 6 steps. We will first set up the environment for running SageMaker Geospatial, and then we will query the data. Once we have the data collected, we will start an Earth observation job to identify the water body in Lake Mead. And then we will see the results in the Foursquare Studio. Once we verify the results, we will extract the land cover segmentation results and actually calculate lake surface area. With that, the first step, we will set up the SageMaker Geospatial capabilities, which is pretty standard. All you need is to initialize a Bodo client in the supported AWS region using the service name SageMaker Geospatial. Once we have the SageMaker Geospatial set up, we will look at the data. We need to get the satellite images around the Lake Mead area. Instead of spending weeks to collect data from different vendors, providers, I can simply use a data identifier to select the Sentinel-2 image. SageMaker Geospatial now has built-in dataset for Landsat 8 and Sentinel-2. Sentinel-2 provides global coverage of the Earth surface at a 10-meter resolution every 5 days. The archive dates back to January 2017. To narrow down our search area, we can simply define an area of interest, AOI for short, which is specified by GPS coordinates, latitude and longitude. In this case, we will use a bounding box that covers Lake Mead area, as you can see in this screenshot. But there's a problem. Clouds may cover the area we're observing, making it really hard to see what's actually on the ground. For that, SageMaker Geospatial offers a really handy data filter for cloud coverage. In this case, we will set the upper bound of the cloud coverage to 1%, so we can get extremely clean images looking at the Lake Mead area. Once we define all these data filters, we can submit a query. SageMaker Geospatial will return all the useful information of the data, like when the data is collected, where's the data boundary, as well as a hyperlink to download the data. Now we get the data we need. We will kick off an Earth observation job to identify land cover types around the Lake Mead area. Rather than spending like months or even quarters, years to develop a machine learning model to classify all the land cover types, SageMaker Geospatial simply offers you pre-trained models to classify all the land cover types. Land cover segmentation is essentially a semantic segmentation. It will classify each pixel of your image into a set of predefined land cover types, such as vegetation, developed area, as well as like snow and ice. As you can see in this example, this is a Sentinel-2 image around the Seattle, Washington area. And the bright yellow color stands for water. And this cirrus cloud and sync cloud are represented by the dark green. You can also see some snow, which is represented by this reddish color. With SageMaker Geospatial, you don't need to build, for this land cover segmentation, you don't need to build your model, you don't need to put in open source model. We can simply call the built-in pre-trained model. All I need to do is using the same data query as I showed above, given the area of interest, define the time range. This time we will look at data from January 2021 to July 2022. We use the cloud filter to look at the clean image, and we will initialize this Earth observation job calling the land cover segmentation model. I can also give a name so that I don't mix up different jobs. This is important, especially if I run in multiple jobs at different locations at the same time. Once you kick off the job, SageMaker will do everything under the hood. You will pull in all the data, met all the filtering conditions. You will only download those images, run with the compute instance with necessary storage. You will only look at the data that's with low cloud coverage. You will pre-process the data into a format that is ready for model inference. Once the data is in that state, SageMaker Geospatial will automatically run the model inference for you. Depends on the workload. In this case, it's the number of images. An EOJ may take you a few minutes to several hours to finish. While you're waiting, you can grab a coffee or go out for a walk. You can also use this Get Earth observation job to monitor your job status. Or you can use list observation jobs to see all the jobs in your team in your account. Once you have a job marked as completed, we can check the results with visualization. In this example, I will pick a job I pre-run with the same configuration we just showed above. For that, I will initialize a map client with this SageMaker Geospatial. I will first render a base map. As you can see, this is a base map centered in the San Francisco area. Next, I will zoom in to the study area by this single line of code, visualize EOJ AOI. This will automatically retrieve the area of interest defined in your data query and show a bounding box on the map as a vector layer. Next, I will bring up the input image. For that, I can use the visualize EOJ input function. Since there are 30 images from January 2021 to July 2022, I can even use a time range filter to select the image I want to see on a specific date. In this case, I will pick the latest image from July 2022. I can also give these map layers a name called input so that I don't mixing up different layers. This is something you will get with this Foursquare Studio visualization, which you don't get with Jupyter widget. So I can do the layer management. Now that I have the input image rendered on the interactive map, I can add output. I overlay the output model inference results with the input image so I can check whether my model recognized the water body in the Lake Mead surface area. So for the output, I will use the same time range filter as for the input layer so that I can match the model output with the input. As you can see, this model inference results start to show up on the interactive map as a single map layer. Line cover segmentation essentially classifies each pixel to a common line cover type. So each pixel has a unique label. In this case, water is represented by this bright yellow color. So if I change in the opacity of this output mask, you can see this bright yellow color aligns well with the underlying water body, which means the line cover model recognizes water in the Sentinel-2 image, which is what we want. We want a measured surface area so I can calculate the area. Now that I have confirmed model results looks good, I can export all the results to my local SageMaker Studio instance. For that, I can use the export Earth observation job. It allows me to download all the land cover mask to an S3 bucket. All I need to do is simply specify a S3 URI. Instead of crawling hundreds of files in S3, I can share these kind of results with my team with a single job arm. Also, grouping things using job arm will make it convenient for dataset management. Every EOJ becomes a data asset in your data catalog. Another benefit of this export Earth observation job is it not only allows me to download the model outputs, but also the input images. These images can be saved for future use for your other applications. Since in this case, we only need the land cover mask to calculate the area, we will set the export source images to false. Same as a model inference job, you can also use the get Earth observation job to monitor your export job status. With all the SageMaker Geospatial capabilities, we were able to identify the water body in Lake Mead. Now I'm going to show you how you can use open source libraries to measure the surface area. For that, I will use the AboutAIM client to download all the data into my local instance. Once I have the data downloaded, I can actually extract the surface boundaries and calculate the surface area. Sentinel-2 L2A images has spatial resolution at 10 meters, 20 meters, and 60 meters, depending on which band you're looking at. During the model inference, all the bands are downsampled to 60 meters. So each pixel in the output mask stands for 3,600 square meters, or 0.0036 square kilometer ground area. So in the land cover mask, each pixel has a value between 0 and 11, stands for 12 common land cover types, Water has a class index 6. So we can extract a water mask by ignoring all the other classes. Once we have the water mask, we will count the number of pixels that are marked as water, times that with the area covered by each pixel, which is what you can see in this lake area. Once we extract the lake area for every single timestamp, we will plot them out along the timeline, as you can see in this plot. So in the last 2 years, Lake Mead surface area has dropped from more than 300 square kilometers to less than 250 square kilometers. If we look closely, during the spring season, February, and we see the surface area is over 300. When we look at the same time frame in 2022, you will see less than 250 square kilometers. That's around 80% drop in surface area. If we look at the summer season, in July 2021, you will see the surface area is about 279, but dropped to only 243 square kilometers in 2022. That's a 30% drop in just a year time. To better communicate and visualize these results, we can also extract the surface boundaries and overlay them with the input images, as you can see in this animation. Notice there's a clear shrink in the north shoreline. You'll also see some shrinks in the southwest shoreline, southeast, I'm sorry. So with that, there you have it. We have explored the SageMaker Geospatial capabilities by walking through a demo for monitoring the lake shoreline. You can also see our launch blog to see a guide how to use SageMaker Geospatial, or check another blog on digital farming. We will give out the blog post link at the end of the presentation. Up next, we will have Damian to show you how you can use these technologies in live for real applications in Arup.
Hi, my name is Damian McLeod. That's me. I'm here from Arup. I'm going to talk about how we use SageMaker through the test process, working closely with the SageMaker team to understand the urban heat island effect and be able to provide actionable insight to developers, to master planners, to landowners. Just to introduce myself quickly, I'm Damian McLeod. I'm the director for Geospatial and Earth Observation at Arup. Have an honorary professorship in geospatial and been working in the industry for over 23 years. So just to kind of set context, Arup is a British company based out of London, but we are 16,000 people. We work across 90 different disciplines. We have 90 offices across 35 different countries, and we run at any one time around 10,000 projects in around 140 countries. So we kind of have sustainability at the heart of everything. It drives what we want to be as our company. It's in our DNA. It's where we want to be. It's what we want to be delivering. So just to kind of give a flavor of some of the projects that we've delivered in the last year or two that have used the data that Amit was talking about earlier. So if we start on the left, Sponge Cities, this was driven by Earth observation data. And we looked at around 30, 40 cities globally to understand their permeability, to understand how resilient they would be to a flood event. What's the absorption? Where's the impermeable versus permeable ratio? And just to understand cities. And we've been doing that across the globe. And there's a link on the arup.com website if you want to know more. Scale. Scale is our tool that we've built for the government in the UK and the state owners to understand where best and how to best place offshore wind farms. This has been such well received that it was spoken about at COP27. And this is about delivering multiple scenarios of data, vast quantities of open data, vector data, raster data, Earth observation data, bringing it all together just to give that insight that people can use at the end of it. And the key thing for all of these projects is that there's actionable insight at the end. We're addressing the so what question with the domain expertise that we hold within Arup. And the one on the very end, bionet gain and habitat surveys. More and more often, nature is the key element. That kind of nature capital is what's being talked about globally more and more. We're able to, and have done across many major projects in the UK and globally, do our habitat survey, so we don't have to put, before we can get ecologists on the ground, we can do a habitat survey and understand what the bionet gain could be for a project, which moves the decision point of where we can take the habitat surveys and potential bionet gain estimates into the site selection process. Therefore, ultimately bringing environment choices at the start of the project rather than further along, meaning better environmental outcomes. So just to move into the kind of projects that we talk about today. So urban areas experience warmer temperatures. We know this, but to what degree? How does that happen? How does it manifest? How do we understand it? How can we understand it better? So just the first graph is around just showing the increase. We all know about climate change and global warming. This just gives an indication of the scale that we're looking at. And the degree can make such a huge difference. In the economic slide, overheating cities face climate change costs. How to deal with it, tarmac melting, how to deal with the infirm who are affected increasingly so by the heat. And just a quick stat on the end, the West Midlands is a region in the UK, and 52% of the heat-related deaths that occurred during August 23 were because of the heat wave, this heat event that we had in the UK when it wasn't grey for a change. So we've created this platform that looks and brings together vast quantities of data around the urban heat island effect to help us understand it. Now, looking at urban heat islands isn't a new thing. I had an article published over 10 years ago, but the difference between then and now is we used one layer of data then, which was land surface temperature. What we are delivering here brings together vast quantities of lots of different types of data to able to understand the space better. So what you have on the left-hand side, the kind of sliders, is looking at different facets of the data, albedo, kind of amount of vegetation. So albedo, how reflective is the surface? Vegetation has a big driver in how a city reacts to a heat event. So it could be, so to take a statistic, the difference between a tree-lined street and a non-tree-lined street can be 2 degrees in a heat event, and that becomes a really powerful mechanism to understand around space. And building emissions, building heights, shadows, having all of these data sets brought together is really key to understand it, to provide actionable insights that master planners can use and understand. So we created this platform to understand what is that urban heat island effect, the contributing factors, and create this index that allows us to model and look at what different interventions can do and how they can work together to bring that temperature down and mitigate kind of the climate change that is happening. So we worked with SageMaker, and the biggest thing that allowed us to do was to operate scale geographically and temporally at a level that we hadn't done previously. So bringing vast quantities of slices of data from different time periods, bringing much higher resolution data into the piece that we couldn't do previously. We were looking at it at a coarse scale before. Now we can get into that building level, that street level, and understand how all of these things fit together to create that effect. If we understand that, we can understand how the mitigation work and play with the sliders, such on the previous screen, to deliver. And this is a mixture of open and proprietary data that we were able to bring in. Some of it was our own data sets, some of it was open data sets, some of it was Sentinel data straight off the SageMaker service. Having pre-trained models within there saves a host of time. The cloud masking, incredibly powerful. But being able to bring in our own models, our own IP into this was increasingly important as the project went on. And be able to visualize at scale and speed as we tested the process and went through these iterations was just an amazing function and facility to have at our fingertips. So the outcome, kind of like, as it says up there, but the speed we could go from having this, going from our ideation phase that we need to build this, we need to understand this, and working with our environmental physicists to building it and to having this solution functioning in some form in 12 weeks was a big sea change, was a big kind of transformation for us as a company. Being able to add the layers simultaneously, being able to make that insights and actionable insight come out at speed in a way that's usable for us, that we can interpret, really powerful, really important. And the reduction of time across all of these, from hours to minutes, makes it a service that we can offer and think about almost as a SaaS service moving further down the line. So the key takeaways that we had is about the improving of accuracy, bringing more triangulation points into the process to help us understand more. Previously, we were limited by our processes and the time to answer, but now we can bring in vast quantities of data. The more data we can get in that we trust, the more robust our answer out, therefore the more robust insight and advisory services we can provide atop of this. The ultimate end game for this is that our environmental physicists, master planners, can provide the advice that's needed to the developers, to the landowners, to help them mitigate and manage the urban heat island effect. We're able to increase our data science and the geodata science team's productivity by having all of the stuff, such as the cloud masking I mentioned before, because that's the killer. Having to do these every single time, having those there was one of the big gains for us on this project. And then just the accelerated adoption by having a single spine to what we're doing, not having code libraries here, there, and everywhere, and the wonder of the C drive holding us all back. It was all there, one place, which means we were able to train our staff, which means we're able to have consistency, it means we're able to drive new workflows and build around that. And that was incredibly important and one of the key outcomes and takeaways for us.